Hello everyone. I'm Kumiyuki from Kyoto University. In this talk, I'll introduce our work, Olive Oblivious Spirit Running on Trusted Execution Environments against the risk of specification. This is a simple summary of our work. In this work, as shown in this figure, we consider a typical scenario of Spirit running using TE in untrusted aggregation server. The problem we address here is privacy risk of side channels in this setting. And we demonstrate that specified parameter can cause privacy leak and propose efficient oblivious defensive mechanism against it. This is a summary of our work. First, I'll start with research background. Here is a brief introduction of trusted execution environment, TE in short. Basically, TE enables secure computation on untrusted remote machines. As shown in the figure, in the security model of TE, we can assume OS or hypervisor in the untrusted server can be compromised by an adversary. But TE is an isolated environment against them. It is basically achieved by special hardware functionality like IntelSGX. IntelSGX is one of the most popular TE implementations and provides memory encryption and remote attestation and so on. In spite of these security features, many studies have shown that TE has vulnerabilities, especially memory access pattern leakage via side channels is serious, regardless of the memory encryption. For example, the prime plus probe attack using the shared cache of CPU is a well-known attack. So in the end, we should assume all of memory access patterns might be leaked, even if we use DE. And this is an overview of Federated Running. FL is a collaborative machine learning scheme with many participants who have their own training data and a central aggregation server here. They train a single global model by exchanging participants' locally trained model instead of sharing their training dataset itself. And the problem in this scheme is that the server can basically see the raw parameters from the participants, and which is known to be sufficient to leak privacy information of the participants. To solve the privacy problem in Federated Running, the combination of FL and server-side TE has attracted attentions. As shown in this figure, the shared parameters can be hidden by the encryption provided by TE, which is guaranteed to be decrypted only in the verified TE. Inside the TE, we can securely perform the aggregation operation. And moreover, the combination of central differential privacy and this scheme can improve the utility of differential private FL, which could be another motivation of FL with server-side DE. And the problem we want to address in this scheme is the impact of side channels. As I mentioned, the memory access patterns can be leaked by different attacks. However, it is still unknown what is specific privacy risks and what is practical protection against the attacks in this setting. So the contributions of this work can be summarized as follows. In FL with DE, we study both of attack and defense in terms of memory access pattern leaks. For the attack, we show that specified parameters, which is often used in Federated Running, can leak sensitive information via memory access patterns and demonstrate that privacy attacks are possible. And for defense, we design an efficient oblivious aggregation algorithm and evaluate the method on real-world scales. Okay, next, I'll talk about attacks. Firstly, this slide shows the analysis on the memory access patterns caused from the aggregation operation of FL within TE. The point is that specified parameters can cause date-dependent access pattern during the aggregation operation. Firstly, we suppose parameter is dense. Let me skip the details, but we can see the memory access pattern is independent from the parameters itself. The access pattern is always the same, like this. But interestingly, we found that in specified setting, the memory access pattern can leak the selected parameter indices. In Federated running, parameter specification is often used, especially date-dependent top-care specification is used for better communication cost and also better utility. Then, considering the aggregation operation with this specification, the access pattern depends on the specified indices like this, because it requires to access the corresponding memory of final aggregated parameters like this. Then, based on the observation, we designed an attack method to show that the leaked information, as I mentioned earlier, can leak private information. The goal of the attack is to infer the sensitive label set of the target participant. The overview of the attack is shown in the figure. In attack, the attacker is mainly assumed to access global test data set and aggregated model of each round. And first, the attacker trains classifier for each round. It takes parameter indices as input and outputs the scores for each level. And second, the attacker observes memory access patterns via the side channels and extract parameter indices for each target participant. And then, using the classifier, attacker infers the label set of the target participant. Okay. The intention behind this attack is that the observable specified indices has correlation with sensitive labels. To demonstrate the effectiveness of the attack, we conducted the experiments with this setup. The evaluation metrics are OR and top one. These show the success rate of the inference attacks. OR means the inferred label set is exactly matched with target label set. So it's kind of difficult. And top one means number one scored label is included in the target label set. It's going to be weakest privacy leak. This is one of the results from the experiment using Cypher10 and MLP model. In the figure, x-axis indicates the number of labels of each participant, and y-axis indicates the success rate of the attacks. And overall, these upper side results shows top one, and inferring the top one label is very easy. And surprisingly, inferring the exact oral label set is also possible. For example, when the number of target label is 3, the success rate is over 90%. And even when the number of target label is 9, the success rate is about 15%. And this attack, the performance of this attack is getting higher when the parameter is more sparse. In these figures, x-axis indicates the sparse ratio. For Cypher 100, we have 100 class levels, which makes the attack more challenging. But as sparse ratio is smaller, like this, for example, less than 1%, the success rate is almost 100%. So overall, the experimental results highlights the attack is possible, and we need some defense method against this attack. And lastly, let me introduce defense mechanism. To protect the memory access patterns from side channels, it is sufficient to make the memory access pattern independent of the input values, because then the attacker cannot know anything from the memory access patterns. This kind of algorithm is called oblivious algorithm. To that end, we can design the oblivious algorithm for the aggregation operation within TE. Firstly, non-oblivious method can be like this figure. We have nk dimensional parameters here, which is concatenated parameters from participants, and the d-dimensional aggregated parameters here. To aggregate the parameters, for every single parameter, we just access a single memory address of aggregated parameters like this. So the total complexity is order nk. And we can make it oblivious by following full memory access approach, which we call baseline method. Like this figure, when updating every single parameter, we always access all of memory address like this, so that we hide the true memory access. And it causes large overheads, but in the end, this algorithm is oblivious, but the complexity is order nkd, which is very large. So we would like to make more efficient oblivious algorithm for this purpose. Then we design an advanced algorithm. This algorithm employs oblivious sort and so on instead of full memory access approach, which reduces the entire complexity compared to baseline method like this. The overview of the algorithm is in the next page. Intuitively, to eliminate input-dependent memory access patterns on the aggregated parameters, at first, we concatenate their initialized full parameters like this, and perform oblivious sort, so that in the next phase, we can aggregate the values by linear access like this, which we call oblivious fold. This allows efficient aggregation while being oblivious. And finally, we perform oblivious sort again and get aggregated parameters like this. And lastly, we evaluate the proposed algorithm compared to non-oblivious method and Passoran-based method, as well as baseline and the proposed advanced algorithm. The figure shows the execution time for the aggregation operation, and x-axis indicates the number of parameters of the global model, and y-axis is the log scale of the execution time. And our proposed advanced method is light green and faster than the other baseline method like this. And also the method is reasonably fast, even in real world scale, like over millions of parameters. Okay, this is the conclusion of our work. That's all. Thank you.